Alright, so in this video I would like to really talk about the molecular orbital theory. And before diving straight into the topic, I would like to take a moment to explore the historical development of this fundamental concept in chemistry. So our journey begins in the early 20th century with the advent of quantum mechanics. We've got people like Niels Bohr and Werner Heisenberg who laid the foundation for understanding atomic structure and behavior. Then, in 1927, Friedrich Hund and Robert S. Mulliken introduced the idea of molecular orbitals, proposing that atomic orbitals combine to form molecular orbitals that span the entire molecule. This was actually a significant shift from the earlier Valence Bond Theory, which suggested that localized electrons between atoms were literally confined in their own space and that they could not move. This work actually paved the way for a more comprehensive understanding of molecular bonding and electronic structure. So we actually have Werner Heisenberg in this picture, as well as Friedrich Hund and Robert S. Mulliken. So Werner Heisenberg is right over here. So that's Heisenberg. And then we have got Hund right over here. That's our Friedrich Hund, who also proposed the popular Hund rule. And over here we have got Mulliken. So that's actually a backstory of the molecular orbital theory. So basically in the molecular orbital theory, the valence electrons are suggested to be delocalized over the entire molecule and not just confined to individual atoms or bonds. So before we start into the deep stuff, I would like to give a little bit of review of what we are already expected to know. So let's start with a quick review of atomic orbitals and electronic configuration. So what does the term orbital even mean? Orbital also is referred to as the wave function. Wave function as in the probability of finding an electron at a certain space, okay? So we are also referred to as the wave function using this symbol. So molecular orbitals or wave functions arise from adding together or superimposing. That's a cool concept, superimposing. That's what we do to waves, and this is a wave function, so that's exactly what we're doing. So superimposing atomic orbitals, okay? So a linear combination of atomic orbitals creates molecular orbitals. And the cool part about that is we also have bonding and anti-bonding orbitals. So yeah, so a lot of stuff there. So I like to start with this concept of linear combination of atomic orbitals. So in short, we actually refer to as LCOW. Sounds a bit weird, but yeah. So now, bonding orbitals. First, let's start with bonding orbitals. So this lecture is going to be divided into 3 segments. First, we're going to talk about homonuclear diatomic molecules. So, and their molecular orbitals will be originating from the s orbital. We know we have got s, p, d, and f orbitals. We won't be going to the d and f orbitals because that's not where it leads us to. And we're next going to talk about the homonuclear diatomic molecules with their molecular orbitals originating from the s and p orbitals. So px, py, and pz. And then we're going to talk about, lastly, the heteronuclear diatomic molecules. Alright, so before I get into all this, let's just review a little bit of quick things. So atomic orbitals, let me just quickly change the pen. So atomic orbitals, we've got S, P, D, and F. Describe the regions around the nucleus where electrons are likely to be found. And the arrangement of these electrons in these orbitals follows the principles of AUF, BAU, the Pauli exclusion, and the Hunt rule. So that are things that we already know and which is needed to proceed with this lecture today. So keeping this a little aside, we're gonna talk about bonding orbitals now. So yeah, bonding, like I mentioned before, we have two kinds of orbitals: bonding orbitals, like bonding molecular orbitals, and anti-bonding molecular orbitals. Now bonding orbital actually forms from the linear combination of atomic orbitals when there is constructive interference. They form from constructive. So, for example, if we know that these are orbitals, so wave functions, and they act as waves, okay? So, for example, we have got a orbital, and we've got another orbital. And if we join them together, okay? So if we join them together, for example, 1s, and as I mentioned earlier, we're gonna first talk about the s orbital, and then we're gonna proceed to the p orbital. This is 1s, and this is 1s, though it doesn't quite look like a 1, but it is. So these are our atomic orbitals, okay? Atomic orbitals. Now, as I mentioned earlier, the molecular orbital theory suggests that when you combine these two atomic orbitals, we're supposed to get a molecular orbital. So for n atomic orbitals, we get n molecular orbitals, okay? So from constructive interference means they come together, we're gonna get a bigger thing. So something like this. Okay, like very ovally and cool shape. So we have our nuclei right in the middle. So nuclei, and the nuclei for the molecular orbital is going to be here and here. Now we refer to the molecular orbital, which is this, the molecular orbital. Takes me a lot of time to write our list. The molecular orbital is referred to as sigma s. Sigma s. Alright, so now sigma s is actually the molecular orbital that you're seeing right now. Why sigma? Because it is cylindrically symmetric about the bond axis, okay? So the definition of sigma s is actually that it is cylindrically symmetrical. Now, what do we mean by cylindrically symmetrical? That means it's like a sphere and it's symmetric. You know, spheres are symmetric. symmetrical about the bond axis. So there are no nodal planes along the bond axis. That means you're supposed to get electrons. You can find electrons really easily along the bond axis. Alright, cool, awesome. Let's move on. So, as we've discussed earlier, we can now conclude that if we combine one SA, basically orbital A, atomic orbital A plus atomic orbital B, we're supposed to get a molecular orbital which is called sigma 1s. And this, my friends, is a bonding molecular orbital, okay? A bonding. A bonding molecular okay. So the main thing that's happening here is something I like to show you. So we've got our atomic orbitals right here, and we know that they are gonna interact constructively. That means they're gonna come together, okay? And what happens when these waves interfere constructively, the amplitude actually increases as they overlap, okay? So this overlap creates a bonding orbital, sigma 1s, with a lower energy, and an anti-bonding orbital, which we're gonna talk about later, with higher energy, okay? These electrons preferentially occupy the bonding orbital, stabilizing the molecule. So right here, we're gonna have an increased amplitude. So this is our nuclei, 1, 2, right over here. So this is positive, this is positive, because these are nuclei. And these are our amplitudes. Okay? Now, the cool thing happens now. So, when these constructively interfere, the amplitude's gonna get like quite bigger. Ooh, that looks like Batman. So yeah, it gets like bigger. It gets like bigger, and there's increased amplitude in the internuclear region, which translates to, an enhanced probability density, which is basically the wave function squared. So there's an increased probability that we're going to find an electron near or between the two nuclei. So it's basically this kind of sweet spot. They're going to be like hanging out right in the middle of these positive nuclei. All right, cool. Now we're going to talk about the energy interactions, which is the energy of a bonding orbital is actually decreased when we're comparing it to an atomic orbital, okay? And that is what actually makes the atom stable altogether. So, for example, let's first draw our energy. That's our energy. Ouch, what did it just do? Okay, this works fine. So the energy, and we have got okay, you know what? I should color code this. So let this be okay. Atomic orbital A and atomic orbital B. They're gonna be together, and then we're gonna have our molecular orbital, which is sigma 1s. Alright, okay, that's a little bit slanted, does not look good. So yeah, perfect. So, yep, so this is our energy. And this is our 1sa, this is our 1sb, and this is sigma 1s, the molecular orbital, when they, interfere constructively. And again, we're just talking about bonding right now. Bonding, okay? Just keep that in the back of your head. So, if we're talking about hydrogen, hydrogen's cool. It's very important, so we talk about it everywhere. So hydrogen. If we're talking about hydrogen, so hydrogen has 1 electron, right? So 1 electron, 1. So this is, it's got 1 electron. Alright, so this is 1 orbital, and this is another atomic orbital. Alright? So this is actually 1 hydrogen, and this is the other hydrogen. And when these two hydrogens, they come together, they make these two atomic orbitals come together, hydrogen atomic orbitals, we get the hydrogen, okay? So, yeah. Okay, so these electrons will now go here, so to form a lower energy molecular orbital. So for hydrogen, when it's 2 electrons, both of them occupy the bonding orbital, the molecule is actually lower energy, so more stable, okay? So there's no anti-bonding pair of electrons which is generating in case of hydrogen. So it's very, very stable. Hydrogen loves to be a molecule and exists like it does. Alright? So now we're going to consider anti-bonding orbitals. I gave you a little bit of hints about what it actually was. So we're going to now talk about anti-bonding. Ooh, that's thick of a pen, but yeah. Anti-bonding. Alright. So anti-bonding orbitals arise from the destructive interference. So when you're having a linear combination of atomic orbitals and they interfere destructively, we are getting anti-bonding orbitals. So similarly, just like we got constructive interference, we're gonna have destructive interference, right? Because these are wave functions, these are orbitals are wave functions are orbitals. So, but there's a little twist in this case. We're just gonna subtract these, okay? So let me just try to demonstrate by drawing it for you a little bit. So this is our 1 atomic orbital, this is our atomic orbital B. And we're just gonna minus each other and get the molecular orbital because they are interacting destructively. So these are just gonna, subtract. And we're gonna get a molecular orbital that looks kinda like this. Alright? So our nuclei will be right in the middle. Here and here, okay? These are our nuclei in the middle. And when we subtract them, we are getting this molecular orbital. Okay, So again, let me just label this one as A and one as B. When these interfere destructively, they cancel each other out to form this molecular orbital. Okay, so the equation that we can write for this is basically 1sa minus 1sb gives us sigma 1s star. Okay, so it gives you a star. So we call this anti-bonding molecular orbital, we refer to it as sigma 1s star because it's still cylindrically symmetrical, but it's anti-bonding because it's interfering destructively, so we call it sigma 1s star. So this is actually an anti-bonding molecular orbital. If I want to demonstrate this further, I'm just gonna draw something like this, a straight line. Our nuclei, they're interfering, okay? They're like interfering destructively, of course. And when they do that, the amplitude, something queer happens to the amplitude. The amplitude will actually decrease, okay? So the amplitude will actually decrease. Got our nuclei here and here. What will happen to the main nuclei? What will happen to the amplitude is that it will decrease. Okay, so I've drawn this. So mainly the amplitude, what happens is like this. Okay, wait, sorry, my PC is actually not quite behaving today. This and this. Okay, so when we get them together, the main result is basically a decrease in the amplitude. Okay, a decrease in the amplitude. Alright, cool. So again, this was our 1s, 1sa and 1sb. Alright. So if the amplitude decreases, it means that there's a reduced probability density or wave function squared between the nuclei and a node between the two nuclei. So there will be a node right between the two nuclei. Okay, the node will be right here. Okay, this is gonna be our node. That means there will be no probability whatsoever of finding an electron right over here. So an electron in this anti-bonding orbital would essentially be, excluded from the internuclear region and will therefore have a higher energy than if it were in the atomic orbital. So now if we kind of talk about our energy, the resultant energy, or the energy interaction, whatever you call it, resultant energy, we can draw a cool diagram again for hydrogen because that's important. Hydrogen is very cool, so yeah, I love hydrogen. So this is 1sa, this is 1sb, this is sigma 1s, and this is sigma 1s star because it's anti-bonding, so there's a lesser probability of finding an electron near to the nucleus, so the molecular orbital will be higher energy than the atomic orbital. So it's going to be higher in energy. So we can connect these like this, because that's essentially how these diagrams are drawn. However, with lack of instruments, I'm not able to demonstrate this very well. But yeah, let's try to make it work. Yeah, okay, something like this. So this is our anti-bonding. Anti-bonding orbital. Okay? Yeah. So the anti-bonding orbital will be raised in the energy by the same amount that the bonding orbital was lowered. So this is actually, you can notice, is actually right in the middle, right in the middle. So by the same amount, this and these are equal, even though maybe my diagram isn't perfect, but it's what it's supposed to be. If you're talking about hydrogen, because you should. Hydrogen, we've got one electron, so this is one hydrogen. This is another hydrogen. So we're gonna form this. So again, we're gonna use Hund's rule. We're gonna fill in the same energy, and as we're seeing, there are no more degenerates. We're gonna fill this one first and then jump to the next energy. Okay, we're gonna fill in the lower energy first and then move on to the next energy level. But as we're seeing that before moving on to the next energy level, we have already run out of electrons. So the diagram will look kind of like this. So basically there's no anti-bonding orbital. Right now there is literally no anti-bonding orbital for hydrogen. And this is actually the reason why hydrogen is so stable, okay? It loves to exist as a molecule. It loves to be as a lower energy thing in the universe. So it likes to exist as a molecule because it's lower energy than the atomic orbitals. So if we talk about the electron configuration of hydrogen, I'm just going to write config for short. That will be sigma 1s2. Why 2? Because we've got 2 electrons right here. Okay. Now we can talk about, that was a good example, hydrogen. So let's move on to hydrogen's best friend, helium. Maybe it's not its best friend, but I don't know, just caused it to be best friends. Okay, whatever. Yeah, so we can now move on to helium, because that's pretty cool as well. And I should switch colors, but I don't know. Yeah. Okay. Okay. Perfect. This is our energy. This is our 1SA. This is our 1SB. This is our sigma 1s. And this is our sigma 1s star. Very nice. So we know helium 2 or dihelium as we know it, as chemists call it, because they like to be fancy. So we've got 2 electrons, one up, one down, one spin up, one spin down, because they cannot have the same 4 quantum numbers. So I'm gonna change the color. Okay. So for the bonding orbital, they've got 4 of them. So fill in this first and then jump to the higher energy. 1, 2, and 1, 2. Okay. So we are now seeing that we've got an anti-bonding orbital and a bonding orbital. So, and they have the same energy, right? So what will happen is basically, okay, you know what? Let's just write the electron config first. Pardon me for my illegible handwriting, but yeah. So this will be sigma 1s2, and this time we'll also have an anti-bonding orbital, so this will be sigma 1s star 2. Okay, right over here. Perfect. So it works. So there's actually no gain in energy and no net gain or loss in energy for helium-2 compared to just helium and helium, okay? So this actually raises a really important question, okay? And the question is, so does helium-2 or dihelium actually exist? Well, the answer is a little complicated, but we could come up to the answer of this question by using a tool called the bond order, okay? The bond order. So the way you calculate bond order is basically, so there's a really cool equation you can use for that, which I'm gonna give you. I'm not gonna gatekeep. Maybe because you can also find it through Google, but yeah. So bond order is half of the bonding electrons. We're just going to write E minus for short. And minus, this is actually a minus, the anti-bonding electrons. Okay, perfect. Bond order, cool name. So if you want to calculate, now we can compare helium-2 and hydrogen, and we can predict their existence. So bond orders actually what am I talking about? Like I don't have the word for it. Like it signals if there's a bond or not. So for example, if it's the bond order is 1, it's a single bond. If the bond order is 3, it's a triple bond. If the bond order is 2, it's a double bond, okay? So for helium-2, if we're going to talk about helium-2, the math is quite simple. So half of the bonding electrons, so I cannot find it, wait. For helium-2, so the bonding electrons, so 1, 2, right? Minus the anti-bonding electron, which is also 2. So if someone does the math, the bond order is actually 0. So in theory, dihelium should not exist. Does not exist. But yeah, you could post comments in the video, under the video, saying that it does exist. It has dissociation energy of 0.01 kilojoule per mole. But I could counter argue that actually that's a very small dissociation energy, and that it was actually the weakest chemical bond ever known. So yes, it was discovered in 1993, which was actually not very long ago, since we're talking about quite a things which have been done long ago. But this bond, it does exist, but it is very weak, so we kind of actually ignore it most of the time. If we're talking about hydrogen, that will be half of the bonding electrons, which is 2, minus the anti-bonding electrons, which is 0, gives us cancel, gives us a 1. So there's a single bond, so it does exist. And let me point out that it has a dissociation energy of 432 kilojoule per mole, which is not very strong, but it does exist. So in conclusion, we can conclude that if the bond order is 0, the bond either does not exist in theory, or if it does exist, we find it's a very, very weak bond. Alright, so now we're gonna talk about bigger things. We're talking about the molecular orbitals formed by the linear combination of atomic orbitals for the 2s orbitals, okay? So now, if we're talking about the 2s orbitals, are basically the same as the 1s orbitals, but they're just gonna be bigger in size. So if we're talking about lithium, so this is the energy. This is, okay, I need to make this a little bit bigger. Something's wrong with this. That works. So, this is our first, let's draw our 1s, sigma 1s, sigma 1s star, okay? There will be sigma 2s, 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 sigma 2s star, okay? So let me just really quickly write these in. 1s, sigma 1s. What's a 6? Sigma 1s star. This is sigma 2s, and this is sigma 2s star. Okay, cool. Neat. So for lithium, we know we're trying to make lithium 2. So this is one lithium, and this is the other lithium. So it's got 3 valence. This has got 3 electrons and 1 valence electron. So the valence will be basically 2s, and the other electrons will be in 1s. So 1, 3 electrons, okay? And to erase these, this looks haunted. Okay, what's up with this? Alright. So this is gonna form anti-bonding as well. So this was a bonding. This is gonna form anti-bonding right over here. For this is gonna do the same. However, we have now run out of electrons to fill this shell. So this shell will be empty, okay? So this is actually the diagram for lithium 2. Need to make these, I don't know why. Alright. If you want to calculate the bond order, which I'm just going to write BO for short, it will be literally just half of 1, 2, 3, 4 bonding, right? Bonding minus anti-bonding, just 2. There's no 1 present here. So 4 minus 2 is 2. 2 divided by 2 is 1. So like just 1 here. The electronic configuration will be sigma 1s to sigma 1s star to sigma 2s. Got the other orbital here, okay? And the dissociation energy will be 105 kilojoules per mole. I could keep on talking about examples, but I think that would make the video very lengthy, and I think it's already very lengthy. So we're just gonna talk about now the homonuclear diatomic molecules originating from s and p orbitals, okay? Now let's consider homonuclear diatomic molecules which involves both s and p orbitals, such as that of nitrogen and oxygen, okay? So I need to keep the topic, okay? So the topic is homonuclear. I think I should switch colors, it's very light. Okay. Homonuclear which originates from both s and p orbitals, okay? So we're first going to talk about the bonding orbitals, which are formed by the linear combination of atomic orbitals of 2px and 2py, okay? 2px and 2py, okay? By, of course, constructive interference first. Constructive interference, that means they're gonna form, yep, you guessed it, bonding orbitals. Alright, so the diagrams are gonna look something like this. Got there's going to be, you guessed it, a nodal plane right in the middle. That's our nodal plane, that means there's going to be no probability of finding electron there. So the nucleus for this will be found here, nucleus for this will be found here, and the nuclei when combined together will be like here and here, okay? So this is the nodal plane. So when we combine 2px of A plus 2px of B, we're gonna get something called, okay, let me just write it up, 2px of A plus 2px of B, we're gonna get something called the pi 2px, the 2px pi, okay? Pi is basically an orbital, a molecular orbital. We first talked about the sigma orbital, this is y by the way, okay, y plus 2pyb gives us pi 2py. Alright, so now the pi orbital, the pi you're looking at is actually the molecular orbital with a nodal plane right through the bond axis. So the bond axis is here and the nodal plane is also right through it. Alright. Now we can also have anti-bonding by destructive interference. Like we always do. So they're gonna form okay, cool. Alright. That is not an arrow. Okay. Works. So we are gonna have two nodal planes in this case. If you feel bombarded with information, just hold on. Just kind of hold on, stick with me a little bit, and this will actually feel really easy. So this is actually going to be subtracted from here, and we're going to get a nodal plane right in the middle. So how are we going to draw it? We're going to draw it something like this. I need my smart draw. Okay. This is way too thick. Wait. Like it's gonna be like ovals, okay? And there's gonna be a bond axis right in the middle. It's gonna be a nodal plane also, and another nodal plane right here, okay? My drawing isn't the best, and it's peculiar, I know, but it's kind of gonna look like this. So 2pxa minus 2pxb will give us our beautiful pi 2px star, okay? And same thing with y, okay? So pi 2p y star. Now, you must be thinking, okay, where's PC? So, yep, coming to that. So PC is a little bit complicated. So the bonding orbitals formed by the linear combination of 2pz will be something like this, okay? Got two atomic orbitals. And let me just label the nuclei. So right in the middle, here, and here, okay? So this is gonna be our 2pz of A and 2pz of B. Together, they're gonna form, drum rolls please, sigma 2pz. You may be wondering why sigma, why not pi like the other degenerates. So it's gonna be 2pz. That's because it's gonna be sigma because it's 2pz. That's because it's cylindrically symmetrical with no nodal plane along the bond axis. So this is our bond axis, and there, as you can see, there are no nodal planes. So there's a sweet spot of sneaking an electron in. So this is basically, again, constructive interference. So there's an increased amplitude because increased wave function. So increased probability density between the nuclear. So hence a lower energy molecular orbital. Again, we can also have anti-bonding orbitals form the linear combination of 2pz. So I'm just gonna try to make this simpler. So if you subtract these, what you are gonna get is oh no. Another orbital here, and the nucleus right over here, okay? This is again gonna be sigma 2pz star, okay? Asterisk star. So this destructive interference of the nodal plane will result in a nodal plane right over here and right over here. So there's gonna be two nodal planes. So there will be like higher in energy, so the relative energies of the sigma 2pz will be a lot higher compared to pi 2px or the pi 2py orbitals, and the cool thing is this actually depends on the z of the atoms. So for example, if the z is less than 8, the relative ordering would be like the pi 2px and pi 2py will come first, and then we're gonna have the sigma 2pz. However, if the z is more than or equal to 8, the relative ordering would be like something like pi 2px and pi 2py will be later, and the sigma 2pz will be first, okay? So that is actually how it works, and I'm gonna try to come up with an example, of course, of oxygen, the thing for which life actually kind of exists as we know it. Actually, I need it longer. I'm trying to make the best as I can. Okay. Oh no. Okay. So we are gonna have our, for simplicity, I'm not gonna draw the 1s orbitals right now because it's gonna require a lot of space, and even though I have space, I actually don't have the necessary tools with me right now. So this is the most I can. Actually, okay. Okay, it works. So this is 2pz, 2py, 2px. This is 2px, 2py, 2pz. Okay, so we know that this is gonna form a pi 2px. It's gonna form a pi 2py. Now and this is gonna be sigma 2pz. Sigma, as we know, it will be raised by the same energy, was lowered by the anti-bonding and bonding orbitals. So this will be pi 2px x star pi 2py star, okay? So we're talking about oxygen, the mighty oxygen. So the z of oxygen is 8, right? It's 8. So is equal to 8. So we have got 6 electrons in our outer shell. So we're just talking about valence electrons at this point. So just 6. So to actually, it would be better if I draw it up, you know. Okay, just gonna extend this. Okay. So we also have our sigma 2s, 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 sigma 2s, 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 sigma 2s, sigma 2s star. So in the first, in the s orbital, we've got 1, 2 electrons, 1, 2, and then we follow the Hund's rule and we go like 1, 2, 3, 1, 2, 3, 4, 5. We've got another one. So sorry, wait. So we start with sigma 2s. I messed up with my colors. Oh no. So we start with 2s and we start with 2px using the Hund's rule. So 1, 2, 3, and 4. Okay. So 1, 2, 3, 4, 5, 6. So this is one atom of oxygen. So another is 1, 2, and then jump to the next energy level. This is 2px. So 1, 2, 3. I've got another one left. It's 4. Okay. Now we're gonna distribute these electrons here. So go here and here, and over here we're gonna have 2px. So same energy levels. We still have electrons. We're gonna fill them up, fill them up. Do you know what I did wrong over here? What I did wrong over here was that I filled up the pi 2px over here instead of the sigma 2pz. Alright? So that is something you cannot do. So you always have to fill up the lower energy first, okay? And then jump to the next degenerates, okay? So one here, since these are degenerates. Same energy, so here. So we still have more, so two electrons, so we like here and here. So this is very much how the diagram is. Not very neat, I know. But yeah, if you guys have any confusions, drop it up in the comments and I'll make sure to attend to it. So the cool property of oxygen that we can understand here is that it's a biradical, okay? So it has two lone pairs of electrons, which makes it biradical and hence very reactive. It's ready to react with almost everything. If it were, and it's also paramagnetic because its electrons, the lone pairs, are not paired. If it was like nitrogen, it would have been paired, so it would be called dimagnetic. But for oxygen, it's just paramagnetic, okay? So in the case of oxygen, the Z was equal to 8, and therefore the sigma, the 2pz came first, sigma 2pz came first, and pi px and pi 2py came later, okay? For if I'm not, okay, let's calculate the bond order now. Will be half of bonding minus anti-bonding, which will be 2. So oxygen is, well, a double bond, okay? If you can draw the Lewis structure, that's fantastic. So it has a double bond. So it's pretty strong, a very strong bond. And nitrogen, I don't have the time to discuss because it's already been an hour. It's dimagnetic and it actually has a triple bond. So it's actually a very, very strong, okay? So it has got like eight bonding electrons and 2 anti-bonding, which makes like 3, half of 6 is 3, so a very strong triple bond. So, but nitrogen and oxygen are very important. I thought of discussing nitrogen as well, but I don't think time would cover. So I'm gonna just jump to the last topic, which is gonna take like a few seconds, okay? So we're gonna talk about the heteronuclear diatomic molecules. So it involves atoms of different elements, okay? Alright, so we just talked about like hydrogen, nitrogen, the same kind of one species, but these are going to involve different elements, okay? For example, in carbon monoxide, the molecular orbitals are formed by the combination of carbon and oxygen, okay? Orbitals. And due to the difference in electronegativity, the atomic orbitals will have different energies, which will lead to asymmetric molecular orbitals. And the 2s orbital of oxygen is actually lower in energy than the 2s orbital of carbon, which will affect the energy levels of the resulting molecular orbitals. And this will actually result in a bonding scenario where the carbon monoxide has a triple bond, okay? A triple bond, basically with a bond order of 3 if you calculate it, but the electron density is actually more localized towards the oxygen atom. But if you want to actually calculate it, the relative energy ordering is actually pi 2px and pi 2py. If only the z of both the atoms, okay? In this case, both the atoms is less than 8, okay? And however, if the energy or ordering becomes more than 8, it actually becomes difficult to predict the bond order for either of the atom. So you're gonna have to depend on other things. So you're not gonna be responsible for that. So another cool thing I'd like to talk about is, for example, HF hydrogen fluoride, it involves the 1s orbital of hydrogen and the 2p orbitals of fluorine. So fluorine has a higher electronegativity, so that means its orbitals are going to be lower in energy, which will lead to a bonding molecular orbital that is like a little bit, narrowed or skewed towards fluorine, which will actually result in something called a polar covalent bond. Polar covalent bond, which will have the electron density will be mostly around fluorine because it's, well, more electronegative. That's it actually, and this was actually all I wanted to talk to you about. Thank you for joining in this depth exploration of the molecular orbital theory. Have a good day.